Okay, so this is our last talk before the discussion session, so don't cry yet. This talk, I think, is a little bit a continuity with respect to the previous one, because it's looking at generative mechanisms for the kind of laws that we have been discussing in previous sessions. So thank you for speaking at the end. I think it's a good end.
Yes.
Go ahead.
Okay, so first of all, I would like to thank you for coming for this workshop and giving so many interesting talks. It was a great pleasure to organize this event for me. And let me begin my talk. So, I had an idea that we present a bit ourselves before giving the talk. So some people followed this idea. Some of them did not. So as you probably all know by now, I graduated in physics, and then I did my PhD and habilitation in information theory. And since I abandoned physics, the question that drives my scientific interest is the question about the generative process of natural language. What kind of stochastic process can generate it, and what can we say surely from a mathematical point of view about some abstract properties of this process. So from this point of view, I've been interested in statistical laws of language, but also in measure theoretic probability theory, and information theory, also with some excursions to algorithmic information theory and then computational linguistics. So I've done pretty much, I think. So the plan of this talk is, the topic of this talk is natural language and strong ergodicity. So first, I would like to convey you, to present you the rigorous definition of ergodic and non-ergodic processes. And I will give some examples, easy. Second, I would like to discuss some linguistic interpretation of non-ergodic processes. Namely, this idea concerns that different texts concern different topics, and if frequencies of keywords in a randomly selected text are random variables, then the process must be non-ergodic. And the third topic that I would like to touch is a theorem about facts and words. Namely, if the stochastic process is sufficiently strong and non-ergodic, then we can observe some measurable effects in the statistical behavior of this process. Namely, there is a theorem about facts and words which says that the number of some word-like strings, of distinct word-like strings detected in the process must be greater than the number of distinct random facts that can be inferred from this process, whereas the facts are a bit abstract constructs which measure how much non-ergodic the process is. Okay, so here I would like to say that this topic has been developed by me for 15 years. So I am making some gradual improvements in many different aspects of this theme, and yes. So let me go further. So first, the ergodic processes. If we have first of all, we will be discussing discrete processes. These are simply infinite sequences of discrete random variables. For simplicity, we assume that this is one-sided process which starts at position 1 and can only extend towards the plus infinity. And if we have a string, which is a sequence of values of these random variables, so this can be letters or this can be words, yes. So either from a countable set or from a finite set or a countably infinite set, we define the variables which simply count whether a given string is in a position position I in the sequence this one. So if we have a word, this is one when the variables starting from the ith position assume the values of these letters, and else 0. So the process is called stationary if the expectation of these random variables do not depend on the index I. These expectations are simply the probabilities of strings, because the probability of the indicator function, the expectation of the indicator function, which is this, is the probability of the string. So this is one way of defining stationary process. And now for stationary processes, not necessarily ergodic processes, we have a theorem which is called ergodic theorem, which says that there exist random limits of relative frequencies of strings. So this is, if this counts whether there is a word at a position 1, such a sum is the relative frequency of the word in the infinite sequence. So what we are saying here is that these limits exist with probability 1, but they can be random variables because they are sums of random variables, and they can be a priori random variables. So now the process is called ergodic if these random variables are constant for all words, for any string that we take into account. If this relative frequency is constant, then the process is called ergodic. So let me give a simple example. So if we take a very simple deterministic process that consists of zeros, here are x1, x2, x3, and so on, then this process is ergodic because the relative frequencies of all strings that consist of a sequence of zeros is equal to 1, whereas the relative frequency of all other strings is 0. So we can also have a process that consists of all ones. This is also a deterministic process, and this process is also ergodic for the same reason. But if we take a mixture of these two processes, namely the processes such that we first toss a coin whether we will sample this process or this process. So this is z. If z is equal 0, we sample this one, and if z is equal 1, this is this. Then we obtain a process in which the relative frequency is a random variable because it depends on this initial switch. So this is the simplest intuition. The simplest intuition concerning the distinction between ergodic and non-ergodic processes. So mathematicians love ergodic processes because they have nice statistical properties. Namely, we have this form of circumvergence, and there are many examples of many simple examples of ergodic processes. First of all, if we have a sequence of independent, identically distributed random variables, then this is ergodic. Second, we have if the process is a Markov process, then this process is ergodic if the transition probabilities are bounded above by a constant greater than 0. There are also more. This is a sufficient condition, but it is not necessary condition. And the third class of processes are hidden Markov processes, which are simply functions of Markov processes applied to each position in the process. And this process is ergodic if the underlying Markov process is ergodic. So if this process x is ergodic, then this process y, which is a pointwise function of x, is also ergodic. Now we can proceed towards non-ergodic processes, and there is, as we have said, the process is ergodic when frequencies of any string in a sample in the long run converge to a constant. So now suppose that we take a text in natural language. The thought experiment here is that we are going to a library and we are picking up a book at random, and we are trying to make the experiment by counting the frequencies in a randomly selected book. So here the idea is that books contain keywords which are somehow strongly correlated with the topic of the book. So for instance, this can be a bijection for a text in mathematics, or also in text in biology, in paleontology. So we expect that the frequencies of keywords are some random variables which are with values that depend on the random topic of the text. And since keywords are some strings, this simply some strings, this stochastic process that models the language should not, the generating process should not be ergodic, that is non-ergodic. So by counting keywords we can infer the random text, the topic of the text. So this intuition can be exactly rephrased as a rigorous theorem. So the intuition is that the process is non-ergodic if we can distinguish at least two different topics by a certain procedure of distinguishing the topics in the realization of the process. So the theorem says that the process is non-ergodic if and only if there exists some certain functions from which can be used, and a certain binary variable which assumes the values of 0 and 1 with a with a positive probability, and we have such a condition that when we take any sufficiently long subsequence from the process, then we can predict this using this function. We can predict we can predict the value of this random variable with probability 1 for any block, for any sufficiently long subsequence of the process. That is, if the length of the subsequence tends to infinity, and it holds for any position for any starting position in the process. So the idea here is, you can imagine this as a sort of that this function kind of models our understanding of the text. So when we are given the text, we are doing our best to infer the topic of the text. And we are simply assuming that such a function exists, and it does not depend. It is independent from the, and it is a fixed function. So when we, so the idea is in the end that we are, and this random variable is a kind of this switch that is preselected before we start generating the process. So this condition simply says that we can effectively detect the topic in the text, the random topic in the text. So it turns out that actually the process is non-ergodic if and only if this condition holds. So the binary variable that satisfies this condition will be called a random fact, and the process is ergodic if there exists at least one random fact. So the random fact tells which of two topics the random text is about. Now, there is a simple example of a stochastic process for which we have a infinitely many independent random facts. So this process looks like this. First, we have a sequence of independent random variables, binary, Z1, Z2, Z3, Z4, and so on. These are binary random variables which are independent of each other, identically distributed with a uniform distribution. So it is equal to 0 with probability 1/2, or 1 with probability 1/2, and the same with other random variables. Then we are considering a sequence of natural numbers, K1, of random natural numbers, K2, K3, K4, which are distributed also according to a parallel. So probability that Ki is equal K is proportional to 1 over K raised to the power of alpha, where alpha is greater than 1. So we have a kind of Z-slope here. And the process that I'm going to construct, which I discovered while being a doctoral student, while making a visit as a doctoral student at Santa Fe Institute, is as follows. First, we take a pair. Of random number, and then we take this one of these random facts, which has the index equal to Ki. This is not the ith fact, but Ki's fact. So the idea is that this process is non-ergodic, since we can in fact is non-ergodic, since all these zk can be predicted given a sufficiently long sequence. So a sufficiently long sequence of xi, starting at any position in the process. So the function that predicts them is written here. When we are given a sequence of pairs of Ki, Zi, these are written here as small xi. Then this function simply tells if among these xi there is such a pair K that K is equal to the index of this function, then return Z. And in other case, if there is no such a pair, don't return this. Don't return anything meaningful, namely return 2. So, if we are sampling independently these random natural numbers, then when the sequence of xi becomes sufficiently long, then we can sample any. Then we can sample with a probability tending to 1 the correct value of the fact, this Z. And for this reason, this process is non-ergodic. But this process satisfies a stronger property than simple non-ergodicity, namely it is strongly non-ergodic because we have infinitely many probabilistically independent random facts. And in the following, I will call such a process strongly non-ergodic. As you can see, here there are some certain functions modeled like in the previous theorem that are functions of sequences of symbols, and there is, instead of a single random variable, there's a whole sequence of random variables, which are uniformly distributed on 2-point distribution 0, 1, and we have such a property that we can infer any of this fact using the function with index k, with probability tending to 1 for any starting position in the sequence and any index of the fact. So here another way of looking at this is that now the number of topics that we can detect in such a process is 2 to the number of independent random facts. So as we are countably infinitely many independent facts. So strong non-ergodicity in plain terms corresponds to, in some intuitive sense, corresponds to a continuum of available topics of text. This continuum, of course, is observable only in the limit of infinitely long text. So you cannot infer one of continuum topics just from a finite text. You need many more. Many more observations. So non-ergodicity via continuum of topics. As for natural language, we have an intuition that different texts concern different topics, and the topic of the text can be inferred from the text. So natural language would be strongly non-ergodic if we had both a continuum topics, that the exact topic of an infinitely long text had to be described not by a single variable z here, but rather a sequence of such random variables, and we have a persistence of topics, which is also some important question, that there exist some functions which allow to infer these random facts from any sufficiently long portion, any portion of text, how far we go, regardless how far we go in the process. So now we can see that this model is a certain idealization, because first of all we have assumed that texts are infinitely long. The texts that we encounter in natural language are finite. Even the longest corpus of natural language is always finite. The second problematic thing is that we assume that there exist topics that do not change in an infinitely long text. So we can ask a question: is there any persistent topic of an infinitely long text, namely the text that we would combine by concatenating all books, for instance, written by humankind? Is there any persistent topic in such a collection? So here we can try to argue that maybe it is possible because of the special properties of the physical and cultural environment in which we live in. So we may suppose that this environment, first of all, contains some amount of frozen randomness. By frozen randomness, I understand such a randomness that is caused by some external fluctuation, but which accumulates in the system over time. So if this randomness gets accumulated over time in an unbounded fashion, we may have something like this. We may acquire such a sequence of independent random facts, and then the natural language would be strongly ergodic if first this randomness would get accumulated, and second, if any random fact of this accumulating randomness would be ultimately described by all sufficiently long text. So we would have a sufficiently strong recurrence to the topics that were previously described. So such a thing It's not completely unthinkable, because when we as a humankind are developing in the process of technical progress, we still have to relearn some very basic things in the beginning. I mean, children have to learn language, have to learn how to use tools, how to write, how to speak. So there is although there is probably some stationarity in the evolution of language, there is also some necessity of coming back to what has been already in the past all the time. So the topic of all text could be just the frozen randomness of the environment. And if yes?
Just a little question regarding the use of the word continuum here. So we are still talking about a countable set or a countable amount of
okay,
items?
the continuum appears here in the limit. When you have when we have a x3, this is our model of text.
Yes.
So when we have a finite amount, we can only infer from this some finite amount of independent random facts. So here in the finite text, in the finite text, we cannot distinguish an infinite countably one of countably many one of continuum topics. There must be countably many topics available for finite text. But when we are trying to extrapolate it to infinity, we cannot exclude the possibility that this will also grow unboundedly.
Okay, but does not mean that it would be isomorphic to the real numbers or something. It's
yes, it would be exactly equivalent to a real number, because you can construct a real number such by taking this zk multiplied by 2 to minus k. It's a binary expansion. This is the number whose binary expansion is exactly this sequence. So
okay, yeah. Thank you.
So in this way, you have just a. So in this way, we can also have an alternative definition of a strongly non-ergodic process. Namely, this is a process for which there is a for which this random switch is described by just a single real number in the interval between 0 and 1.
Okay, thank you. No, I understand.
Yes, and from this point of view, not only this Santa Fe process is strongly non-ergodic, but also a simple mixture Bernoulli is strongly non-ergodic. But what I am going to say next is that this mixture Bernoulli process is not is probably not sufficiently strong and non-ergodic to exhibit some interesting property that is probably satisfied by text in natural language. Okay, so yes, I'm going now to tell about theorem about facts and words. So these considerations that we made so far may appear a kind of pure philosophy, which is very hard to test empirically. But it is not exactly. It is not the case. There is a theorem which I discovered how many years ago? More than. Yes, I published the paper in 2011, but I submitted the manuscript in 2008. It waited quite a long in transactions, so I can say that this theorem is about 10 years old. So some version of this theorem, because I've been improving it all the time. So the theorem says that if we have a finite text drawn from any stationary process, then the number of distinct ppm words, I will describe what these exactly are. These are some substrings that are detected by a well-defined mathematical procedure in the text, which somehow imitates the process of distinguishing words in text in natural language. So this number of distinct ppm words must be roughly greater than the number of independent random facts that can be inferred from the text. And the intuition that stays behind this theorem is that rich vocabulary of a text is a necessary consequence of a complex word described in text. We can try to measure the complexity of the word described in the text by the number of these distinct facts that can be inferred from the text. So we would so if we adopt such an understanding of complexity of the text, then this statement becomes less obvious than it is that it may superficially appear. Although if we have some idea that words are some meaningful units of the text, then this relationship may appear intuitive, because you cannot convey sufficiently many meanings without using sufficiently many words, assuming that different words mean different things. So what is also interesting is that converse statement to this theorem is not true. If we have a rich vocabulary, it needn't necessarily apply the high complexity of the described word. So in mathematics, in the mathematical theory, this would correspond to a situation where we can discover many words in the process, but the process itself is not ergodic. It's not non-ergodic. It can be a very simple process in which still this vocabulary grows. Okay, so now the preparation for this theorem. So we have, I will denote the blocks. This is an information theoretic convention of writing blocks as superscript as x subscript from 1 until superscript n. This is just a sequence of random variables from x1 until xn. And the set of independent random facts will be a random variable, which is depending on some subsequence of these, which is depending on some text x1n, and this. Well, this notation is maybe a bit obscure. The idea is that we are taking the first L indices of facts that such that the function for predicting the facts returns the correct fact. So this is the number of facts that can be really inferred from the text. And the second statistic of the text, the second random variable that we are going to investigate, is the set of all substrings of length m in this text x1. So So we are putting a sliding window across the text, and we are simply noting which strings have appeared of the length m, and this is denoted as this. So now the only non-trivial thing on this slide is the ppm order of the text. So ppm algorithm is a certain compression procedure which proceeds by approximating by trying to estimate a Markov model to the text, and it actually estimates not one Markov model of the text, but infinitely many Markov models of growing orders. That is the Markov models of growing dependence on the past. And now the PPM order is the order is this order of the order of this Markov chain, which approximates a given finite text the best, because the lower orders will underfit and the upper orders will overfit. So this is just the best. And the set of distinct PPM words is simply the PPM words are simply the words of the length equal to are simply the substrings of the length equal to this PPM order, which appear in this X1. So here appears this random variable v. V is here. We plug in here instead of m this GPPM X1n, and this is our set of distinct PPM words. So now the theorem about facts and words uses two auxiliary concepts. Namely, first is the mutual information between two blocks of length n. This is one block of the length n, and this is the second block of the length n, which is adjacent to this block. And the second thing is the Hilbert law exponent. The Hilbert law exponent is a power law exponent of a sequence. It is well, when the sequence grows as a power law, then this exponent is simply this exponent of this sequence. But the general mathematical definition is more general. It captures many more cases when this can be, for instance, a stepwise power law growth or something more. And in this case, this definition is the exponent of such a stepwise power law growth. And the theorem about facts and words says that the number that this Hilbert exponent of the number of facts that can be inferred from of the number of random facts that can be inferred from a given text is greater than the power law exponent for the mutual information between this text and the text of the text of the same length appearing after this. And this is smaller than the number of distinct PPM words that appear in the text. So here we can say that the number of random facts that can be predicted from the text is roughly smaller than the number of distinct words that can be detected in the text. And this is a statement about the power law growth of all these quantities, because this Hilbert law exponent is the asymptotic exponent, is the exponent of the asymptotic power law growth of the sequences. So for some type of processes, we have in fact an exact power law. This guy grows like a power law with exponent beta, and the mutual information also grows as exponent with power law, as a power law with exponent beta. By the way, you probably heard of Hilbert's hypothesis, which states that for natural language, this mutual information grows like a power law. And we can see that there is a connection between the theorem of facts and words and Hilbert's hypothesis. So the mutual information is something in between the number of the number of independent facts and the number of PPM words. So what happens for natural language? For natural language, here this is a bit unclear, so let me say what we have in this plot. The first plot is ppm order. This is GPPM. The second plot is the number of the number of distinct ppm words that can be detected in the text. Here we have the length of the text, and here is the ppm order, and here is the number of distinct words. So we have two cases. The first one is the 35 plays by Shakespeare, and for that we have a kind of stepwise. Here we have a kind of stepwise logarithmic growth. And the second thing is the random permutation of characters in Shakespeare. So it's a unigram model, and for this model we have a saturation with this ppm order doesn't grow; it stabilizes here. Whereas for vocabulary, for this number of distinct ppm words, we have a kind of stepwise power law growth for Shakespeare, and we have only a logarithmic growth of the number of distinct words for random permutation, because it's double logarithmic scale here on both axes. Here is logarithmic axis only on this, and here is linear.
Lucas, can I ask, can you connect either the GPPM or the VPPM to the topics or to the number of topics?
Not exactly. This is I will say.
Okay,
so for IID and Markov processes in general, we have that we have no power law growth of the number of distinct ppm words. This is just a logarithmic growth. But for natural language, we seem to have this power law growth with an exponent beta. So now we can ask whether we can. So now the problem is that actually we this inequality can be strict inequality. So all we can say from this is that we have some indirect evidence that language may be stronger than ergodic. Such a hypothesis is not contradictory with what we observe in the data. And moreover, we can hypothesize about the links between the Hilbert's hypothesis and Zev's law. Namely, what we are measuring here was the number of ppm words. ppm words are somewhat shorter than words in natural language, but they are of similar length. So when we observe a power law for so we have a kind of Hebb's law for ppm words, the power law growth, and yes, and this Hebb's law for ppm words is something I think more fundamental than the Hebb's law for words understood as strings of letters delimited by spaces. Because if you take the monkey typing text, it is an IID source, so the number of ppm words will not grow like a power law, but only logarithmically. So here we are observing something a bit stronger than this Hebb's law for words understood as strings of letters delimited by spaces. So in this way, this Higgs law for PPM words seems to be a bit stronger evidence for strong non-ergodicity than just this law. Okay, so the conclusion is the natural language strong and ergodic? As I said, we cannot exclude it, since probably for two reasons. One is the kind of rational reason that we hypothesize that we live in a world full of frozen randomness, which accumulates over time, and we are recurrent to we recur in our description or in our communication to the state of this randomness all the time. And the second thing is that we can by this theorem about accent words we can observe we can make some observations which are not contradictory with the hypothesis of strong non-ergodicity. So this is roughly everything that I wanted to say. I have some additional clarifying remarks which I could answer during the question, which I could refer to during the question. So the question is about understanding how we understand non-ergodic processes and how we distinguish them from ergodic processes. So this depends on our interpretation of probability, whether we adopt a strictly frequentist view which excludes non-ergodic processes, or whether we adopt a Bayesian view in which we put a prior onto probabilities, and then we can observe non-ergodic processes. So maybe I should also mention that now I am trying, as you can see here, there are expectations. Here there is also an expectation, because this is the expectation of minus log probability, and this is the expectation of the pointless mutual information. So what I am interested in now is an attempt to remove these expectations and taking it into an almost sure statement, which would be much stronger because then we could be able to discuss the ergodic components of a process, of a strong ergodic process, rather than just the average case of a non-ergodic process. Okay, so say that it is all.
Yeah, just to see if I understood some things correctly. So these PPM words are the total vocabulary of your Markov process that you are using in a specific range of the text, right?
Yes, yes.
Can I think then these words are defining a topic as these are
well, this is not exactly, the relationship is not exactly in this way. You can have different processes probably that have very similar vocabulary. So this relationship to topic is more complicated, because there was this theorem. Here, if this theorem is easy to prove in one way, namely, if the process is non-ergodic, then there is a string whose frequency converges to a random variable, and then you can construct this random fact as an indicator which says to which frequency of this word we are going to converge, whether it is the higher frequency or a lower frequency. And the way going back, namely showing this theorem in the other direction, is much more complicated. You cannot do it without using measure theory. So this relationship between words and facts is in fact much more subtle than just a simple relationship. Oh, I see this word, and then this is a certain fact, and I see another word, and this is another fact. This is something more subtle that effectively just only the total number of distinct words is bounded below by the number of distinct facts. And as I said, this inequality is strict. So there are processes, mixing processes, for which the number of facts is 0 because these processes are ergodic, but still the mutual information between blocks grows like a power law. So this also makes the number of ppm facts grow like a power law. Yes.
I think what you just presented is extremely beautiful and very, very important. And I'm wondering whether what you're saying is that most of us are wrong, and you probably would be right, in the sense that several of us, myself included, have been proposing the use of many different entropy measures for text, for language. Mm-hmm. And if we take those seriously, apparently those measures are only defined for stationary ergodic processes.
Yes. Well, apparently these measures are okay. It's. I think that that language. I suppose that language is strongly non-ergodic, but these information measures can be quite uniform across different ergodic components of a non-ergodic process. I mean that although the frequencies of the words are random variables, the relative frequencies of words are random variables, when you take into account the entropies, the empirical estimates of these entropies, then they are much less variable. There is much less non-ergodicity in the estimates of entropies. So Kumiko and I did estimation of entropy rates for different languages, or even for the same language. We took the very different corpora of English, and of course we could observe some effects of non-ergodicity that for some corpora the estimates of entropy were a bit different than for others. But I think that these information theoretic measures are much more stable than the raw frequencies of words. So you can say something about language by investigating the information theoretic measures.
But in practical terms, if you had to make recommendations, if you want to make reliable estimations of entropy, or let's say safe estimations of entropy, we should avoid mixing different topics, right? Because that increases the chance that we are tossing coins to decide where to go,
if you want
right?
to do something meaningful, you should collect say sources on different topics and measure both the average measure for all these different topics, as well as variance against these topics. So to somehow state that what you are measuring is not a constant, but rather a random variable with a certain distribution.
So let me see if I understand what you're saying right. So perhaps you could treat language, even if it's not ergodic, as if it were somehow piecewise ergodic.
Yeah, that's also what I understood.
Yeah, that's what traditional topic model does. Yeah.
Yes, that's what traditional topic model does. Yes. Also, I didn't touch the question of stationarity, which arises when you are assuming this piecewise non-ergodicity, because then you are there are different timescales in language, and what you are considering as an effect of non-stationarity or non-ergodicity can be just effect of taking a too short time scale, which could blur out when you take a larger one, unless there is a really a process of some accumulation going in language in the historical terms, which I believe that there is, because our civilization becomes more and more complex. However, we start to measure this complexity. But yes, so.
Yeah, let me further ask to try and, I'm trying to at least grasp like the very shallow concept of this. So, in your examples, you're taking a certain granularity of looking at it. You're saying, if I pull out a book, say, or a specific kind of text, then there is a certain topic, like I do with the Bible, right?
Yes.
Then the word God is all over the place. If I take another text, then there will be other words which are more frequent. So in that sense, at that level of granularity, it's probably true that the topics really strongly influence the probabilities of, or the frequencies of the words, right?
Yes.
But the question I think that you're asking is, if we take 10,000 books,
yes,
are there still 2 times 10,000 books that are different due to a topic?
Yes.
Right.
Yeah. So now that there becomes yes. There is a some philosophical question about this, about the status of probability. That is, whether you are looking whether there is something, whether it's the question whether these books that have been written could have been written in a very different way. Yes, that whether you have it's a question about because if you collect all books that have been written in human language and you concatenate them, then you have just a single sequence. So for this single sequence, you can apply the frequentist interpretation of a probability, and if you apply the frequentist interpretation of probability, you have no non-ergodicity. Because by ergodic theorem, you only see the relative frequency in the sequence. There are no other competing infinite sequences that you could consider.
Yeah, I was thinking about that when doing the chapter.
Can you explain that a bit more? I don't really understand it.
So if you have different books of finite length, yes. So now you can either look at them at such a kind of as you can look at them as independent, as repetitions of some experiment in writing a book, and then you obtain a non-ergodic process because these books are on different topics. Or you can try to concatenate all books like this, and you have just a single sequence, and then you have if you adopt a frequentist interpretation of probability, that probabilities are just the limiting frequencies in the text, then you probably obtain just an ergodic process. If this is stationary, of course, if this is not stationary, then you didn't obtain an ergodic probability.
It's going to depend on which order you put those books on.
Yes.
Yeah, maybe trying to set to the parallels to the ideas of topic models, that at least the word topic is the same as you use here and some a bit more, but there maybe the focus is not these more fundamental questions, but it's essentially how to find a effective short description of the data. Right. So,
yes.
And a crucial issue there is that the number of topics is usually a variable number, right? So, and we would like to know whether how the number of topics needed to describe the database will increase depending on the text size or number of documents, and hopefully they should increase more slowly than the number of words and the number of documents. Can you from your results, find any bounds on the number of topics or on how the number of topics grows from real text?
Yes. This is exactly what the theory about facts and words says, that you cannot infer more of these zi's. Then there is this number. Well, the number of I that k is this is less than the number of ppm words. So if these are independent random variables, then the number of topics is to the power of k, more or less, because you have a book in which this is 0. This is 0, this is 1, this is 0, this is 1, for instance, and you take all possible combinations, and in this way, if you have inferred k independent facts, then you have 2 to the k different topics. So if you have a certain if you have here the number of words, the number of different topics is just is bounded by 2 to the power of different words. It's still it's an extremely large number.
It's hopeless. Yeah.
It's hopeless. Yes.
Yeah,
Yes, but for Bernoulli processes, this grows like a power law. But for Bernoulli process, for instance, you have this grows like logarithm of n. So this number of topics grows only as a power of power of the length of your data. Yes.
Very simply, this is very stupid. What are ppm words? What's
Okay.
ppm start from?
Well, this is a bit complicated, because first you have to define this ppm order. As I said, the ppm words are all strings of length equal to the ppm order that appear in the text. All substrings. You take a window of the length equal to to the optimal Markov model for the text, and you slide it across the text, and you count all possible words. So these are not words in the linguistic sense, but this is some simple mathematical procedure that can approximate something like tokenization in the text.
So it's a closure of the substring relationship, basically.
Yes. So what I try to say is that Heap's law for these ppm words is something from which we can infer more about the process than the Heap's law for the orthography, for the spelling, for the words in the linguistic sense. It conveys some information theoretic and some information theoretic consequences. Yeah.
Okay. Are there any more questions? Okay, we thank him again.